Thank you, Samuda. Thank you, Chris. Thank you for the introduction. And I don't always see when you put your hands up, even on Zoom, so feel free to talk aloud and take over. Okay, so I'll start with this beautiful picture. This is in Cambridge, the other Cambridge. It looks like a very peaceful place. That was a few years ago. Actually, that's where I did my PhD. I took that picture. And you wouldn't know, just staring at it like that, how peaceful it is, that for 700 years, it used to be one of the busiest places on the planet. For 700 years, every year there was what was called the, oops, it's not working. Yeah. Stourbridge Fair. It was the biggest fair in Europe, bringing people from all over Europe. That was happening every year. And rumor had it that that's where Newton actually found his first prism. And you'll see throughout today that Newton prism is really ubiquitous to a lot of science that we do, a lot of research that we do today, going all the way from this very simple experiment, it's almost like a child play, to uncovering some of the mysteries of the universe. So you all seen a prism, you all seen a rainbow. I don't want to insult your intelligence, but you all know, I'm sure, how it works. I'm just going to recap because it's going to be useful for us to see how we can use it to our advantage in a slightly different way. So the idea behind Newton prism, or a prism itself, is that in the vacuum, light travels at a speed of roughly 300,000 kilometers per second. Roughly this, you know what it is in miles per second. I don't know exactly what it is. Actually, something which is quite fun is that the actual value is given here. It's not quite 300,000 kilometers per second. It's exactly that value written in here with no error bars whatsoever. This is it. There's no comma and then error bars or anything like that. There's no other number here because nowadays the notion of a meter is actually defined as the length traveled by light in 1 over this amount of seconds. So in terms of meters per second, or in terms of, now if you want to translate how many miles is how many meters is a mile, it would be, this relation is absolutely exact. So that's how light travels in the vacuum. And the idea of the prism and the rainbow that you see in here is that in a medium like water, like air, like glass, as you see there, then the speed of light actually starts depending on its frequency. And so when light of various superposition of frequencies enter the prism, which is made of a medium of whatever, in here glass, for instance, then it splits between its different frequencies because they don't all travel at the same speed. And then at the exit of the prism, you see the superposition of the color now being spread ever so slightly, which is the idea behind a rainbow. Now we all know that since a child, that something like that happens. We all learn to know that when you see a rainbow in the sky, it means that there's some droplets of water in the sky. There's something there, there's a medium there, which meant that light as it came in, it got into some type of medium, and that's what led to the rainbow. So the question I'd like to ask today is, wouldn't it be amazing if you could do the same thing for gravitational waves? Could there be such a thing as a gravitational rainbow? And if there was such a thing as a gravitational rainbow, it could help us establish the substances that live in our universe. Just imagine gravitational waves propagating through the universe. And if it goes to some type of medium for which the speed of gravitational waves starts changing as it is through this medium, we could in principle see some gravitational waves, and this observation could help us establish what our universe is made out of, what patterns there is in our universe, what medium or what substances is filling our universe. So that would be a huge mystery that we would be able to uncover. Of course, you know that gravitational waves have been detected with a beautiful precision. I mean, this is old now for you. For me, this is very recent. For you, this is all story. In 2015, the event was the first direct detection of gravitational waves. I say it's a direct detection of gravitational waves because there was lots of very strong detection of gravitational waves. People don't call them direct per se, but we knew gravitational waves did exist through other means before that. And the morning after the announcement, that was in 2016, but the morning after the announcement of the first detection of gravitational waves, every newspapers on the planet, sorry, this is, now you can have any pattern you want, gravitational pattern on anything you want, a mask if you want, your scarf or whatever you want. The day after the announcement, every newspapers on the planet announced the detection of gravitational waves and the fact that Einstein was right. That seemed to really seem to be the main point of the main take-home message of the detection of gravitational waves, that Albert Einstein was right. So this is not going to be whether or not he's right or not. It's not really going to be the purpose of this talk, but I think it's nice for you to go through that and understand whether or not he was right and whether or not it is relevant. So let's go a little bit on whether or not Einstein was right through the detection of gravitational waves. So let's go through a little bit of history. Einstein came up with many breakthrough of the past centuries. General relativity is only one of them. There was special relativity 10 years earlier that led him to build the building blocks of general relativity in 1915. Very soon after, in 1918, he introduced the concept of gravitational waves. But quite a few years later, in 1936, him and Rosen, they wrote a paper that they sent for publication to Physics Review with the title, "Do Gravitational Waves Exist? Answer No." This was the third paper by Einstein and Rosen, and at the time Einstein thought that actually the concept of gravitational waves was just a gauge artifact which wouldn't be anything observable, no physical relevance, no matter how precise the experiment was. So the reasoning behind this title, the reasoning behind the paper itself, wasn't about observability per se. It was really about the fact that there was no physical content in those gravitational waves. So you have to, by that time, as you can anticipate, Einstein was pretty well known, pretty famous already. He'd done all of his discoveries. And the idea of peer review, where you send a paper to a journal for it to be published, at the time it was automatic that the paper would be published, particularly if you were Einstein. They had just established the idea that papers should actually be reviewed before they are published in a journal. And to Einstein's great surprise, he got a response from Physics Review. The journal's response in July 1936, which was very, very soon after, was to let him know that there had been some comments made by an external reviewer, by an external referee, and he kindly asked the authors to give them feedback and possibly edit the paper accordingly before being considered for publication. So nowadays this is standard, right? You write a paper, you send it to a journal. You typically get some harsh reviews from the referees. There's 1 or 2 or 3 referees, and they pull your paper apart and tell you to start all over again. This is common practice. At the time, this was the first time Einstein was to deal with this, and he wasn't happy at all. Oops, what happened now? Can you see my screen again? Yeah, okay. So his response wasn't a pleasant one. So this is his response in German. Translated the best I could in English, he says, "We have sent you the manuscript for publication. We haven't authorized you to show it to any specialist, and we see no reason to address in any case erroneous comments by the anonymous expert." Luckily for Einstein, so he tried at that point to send the paper to another journal. Luckily by that point, actually the report was had been given by Robertson. And before his paper in its current format was accepted in the Journal of Franklin Institute, Einstein realized that his proof was wrong, and he communicated with Robertson directly. And he corrected his paper, and finally got published with the correct version that gravitational waves really do exist. So there is some definite positive aspect to peer review, as one would expect. But the bottom line is really the detection of gravitational waves is really not about proving whether Einstein or Robertson or anyone else was right or wrong. It's the beginning of a new era of science. It's really going to open our eyes. It's a new way of communicating with the rest of nature, with the rest of the universe, in a way which had been impossible before. So it's really a new way we can understand everything around us. And this is the beauty in the first direct detection of gravitational waves, much more than proving whether someone was right or wrong. Okay, so what can we do with gravitational waves? There's many different things, and I'm sure you've seeing some of the headlines every so often on new discoveries that are going on with gravitational waves. One aspect I'd like to address, which I alluded to at the beginning, is to understand whether the speed of gravity is fixed or whether it could be variable, and whether we can learn anything from this variation of the speed of gravity. What I mean by the speed of gravity is really the speed of gravitational waves, whether we can learn from that aspect. And I'll hopefully, I'll provoke you a little bit into understanding how significant that could be, and whether it always follows our intuition. So to be a little bit more precise, you don't need to know too much about particle physics for that, but to be a little bit more precise, we think of gravity in Einstein's theory of general relativity. Gravity is mediated by a massless particle, which we call the graviton, very much in the same way as light and the force of electromagnetism is mediated by a massless particle, which is the photon. And simply relying on special relativity itself, massless particles propagate along what we call the light cone. They propagate at a fixed speed. And here now I'm going to set the speed of light in the vacuum, which is 1. Okay, this is the 300,000 kilometers per second, or the slightly modified, corrected version I wrote down before. So this is in the vacuum, and this is in flat space-time. Now we know that for light, when it travels not in the vacuum, when it travels through a medium, it travels at a slightly lower speed. There's some very good reasons for that, which I'll go through later on, and this is related to causality. And this is simply due to the fact that as electromagnetic waves or the photon or light, however you want to call it, it's all the same for me. As it travels through the medium, it starts interacting with the atoms or with the electrons or whatever this medium is made out of. And these interactions actually slow down the propagation of light. So you would think the same thing should happen for gravitational waves. So it should travel at the speed of light in the vacuum. But as we know, we don't live in a boring, empty space with nothing around us in just a flat space. We live in an exciting universe made out of structure, made out of curvature, made out of galaxies, lots of things going on. And so as gravitational waves go through these different media, it's worth understanding whether the speed itself will change or whether gravitational waves will still always travel at the same speed, which is what I mean by the speed of light here is the speed of light as if it was going at infinite frequency and not interacting with anyone else. Okay, so this is the question we like to establish. And really, as I mentioned before, we like to understand whether there could be such a thing as gravitational rainbows, because if we can see how we have a slight modification of the propagation of gravitational waves as it travels through our universe, that could get us some insight of what the universe is made out of. So this is a question I've been exploring with many different collaborators from all over the planet. You see some are in Asia. I haven't written it down here. I have some collaborators in the US, some in Canada, a few in Europe, in the UK, of all ages. And one thing you should see from all of those collaborators, this is just a subset. I couldn't put the picture of everybody. But one thing you should notice is how happy everybody is. So working on this type of topics really makes your day. Okay, so it's everything I'll be talking about for the rest of this talk is really thanks to this subset of amazing collaborators and all the other ones throughout the planet, which I haven't pictured there, but have had immense contributions on everything that we are learning. Okay, so one thing that I'm sure you all know by now, because you're all bright physicists belonging to physics associations, and because it's something really exciting. So since the direct detection of gravitational waves from this black hole merger, and I haven't talked too much about it, I'm happy to talk more about it later on if you like to, but beyond this direct detection of gravitational waves from black hole merger, in the meantime, there's been other sort of events, in particular, the merger of at least a neutron star with either a neutron star or a black hole. But the fact that one of the companions wasn't a black hole is significant, is that in the merger, there's been radiation of electromagnetic waves as well as gravitational waves. And the first such event happened in the summer of 2017. It happened 130 million light years away. So 130 million light years ago, so quite a long time ago. I'm just going to say how much I was in seconds, in light seconds, not because I'm particularly attached to that, but because it's going to be relevant for what we're going to be discussing afterwards. 130 million light years, that corresponds to 10 to the 15 light seconds away. Okay, so that's how far away it was and how long ago it was. Now, throughout this merger, there's been an emission of gravitational waves, and almost instantaneously at the same time, there's been an emission of light. I'm saying almost instantaneously. Actually, light typically gets trapped around this object because it interacts much more with the medium. So it's quite normal to see light slightly after gravitational waves. But actually, when you're considering how far away or how long ago the signals were emitted, it is absolutely remarkable that here on Earth, we were able to detect a gravitational wave signal at time 0. And then within 1 second, we observed electromagnetic signal at huge frequencies, those frequencies. So the fact that it came in 1 second later is really not to be worried about. This is all to be expected because, as I said, light really interacts much more than gravitational waves. You expect it to be trapped until it gets released. So the fact that it came not exactly at the same time is not at all to be disconcerting. What is absolutely remarkable is, given the difference of frequencies between, so all of those electromagnetic waves, all of those is light at different frequencies. I'm just focusing on this one because it's the highest frequency. It's 100 kilo volt as compared to of the order of 100 or 200 hertz. So here I haven't made the conversion between keV and hertz. I can give you that later if you're interested. But this is really huge as compared to hertz. And so really that tells you that the speed of gravitational waves at those frequencies is extremely close, has to be extremely close to that of light at huge frequencies. So to put that into an equation form, the difference between the speed of, this is a t because we call it tensor modes, but this is the speed of gravitational waves as compared to the speed of light, is identical in 1 second. At most, the difference could be at most 1 second over something which is 10 to the 15 seconds away. So that tells you that the speed of gravitational waves is the same as that of light in 1 part to the 15. And as those frequencies, light as those frequencies really are completely insensitive to the curvature of the universe. This is much higher frequencies than the curvature or whatever light was propagating through the universe as it got to us. And interestingly as well, you know, you may think that you understand light extremely well. Actually, to some extent, with respect to some of its properties, we don't understand light as well as we do for gravitational waves now. So for instance, it's not inconceivable that light, the photon itself, could have a small mass. I mentioned before, the photon is a massless particle. Actually, how do I know? All we know is that there's constraints on how heavy the mass of the photon is. And those constraints on the mass of the photon is 10 to the minus 20-ish electron volt. But as those high frequencies, such a mass would be entirely irrelevant, completely irrelevant on the propagation of electromagnetic waves. So at those frequencies, the speed of light is really 1. We can really treat it as 1. And so that gives us a constraint on the speed of gravitational waves at LIGO frequencies to be exactly 1 in 1 part to the 15, 10 to the 60. Now, this is interesting because there's many models, and I'm not going to go through them. We can discuss about it later if you want to. There's a lot of models that predict a different speed of gravitational waves for many reasons. Either because gravitational waves, as I mentioned, may interact with dark energy or all the dark sector as they travel through the universe, or because we may not understand gravity as well as we thought we did, or maybe because the graviton itself has a mass, or various different reasons. And so this observation on the speed of gravitational waves seems to rule out all models of our universe that would otherwise predict a non-luminal speed for gravitational waves by an amount which is larger than 10 to the minus 15. So roughly ruled out anything which is not extremely close to general relativity. And most models of dark energy that had been postulated before, where you have some interactions between gravity and dark energy, could be used to roll out those models. Or do they? So this is something for you to think about, because when you think about it, it is actually normal that when you think of, let's just take the analogy with light. When you think of sending light through a medium, and then you want to make the analogy between sending light through a medium with sending gravitational waves through a medium dark energy, it is normal that for light with a wavelength which is comparable to the relevant scale of the medium, for instance, the separation between the atoms, it is normal that this wavelength or this frequency of light gets affected by the medium. But if you send light with extremely high frequency or extremely short wavelength, then you would expect it to be completely unaffected by the medium being present there. And the speed would be exactly 1. And as that is related to what I mentioned before, for sufficiently high frequency, no matter what is present, if you're really too high frequency, you're always going to think that you are in completely flat space-time, and you're going to be completely unaffected by the presence of the medium being there. So whatever happens, even if you have a model of dark energy or a model of modified gravity, where you expect to have a departure of the luminal speed of gravitational waves, you should always expect by analogy that at sufficiently high frequency, the speed will go back to being exactly luminal. But when you think of the models, for instance, of dark energy that have been proposed, they are models which now we know have to be an exactly 1 speed at LIGO frequencies. This is what I mentioned before, of the order of 100 to 200 hertz or so. But it's not inconceivable that at much lower frequencies, the speed of gravitational waves could be quite different. And this is what happens for a rainbow of light, for anything we know about light. The fact that the speed changes is a function of frequency, and at sufficiently high frequency, it always goes back to being exactly luminal. But now in all the models, for instance, of dark energy, all the models that we're using to describing the late-time behavior of the universe. These are models which are supposed to be valid at very large distances because you want them to be valid on the whole observable universe. And so very large distances correspond to very low frequencies. And therefore, the regime of validity of this model is typically those at very low energy or very low frequency. And so actually in many of those models, it is quite conceivable that they could still predict and they could still be validly predicting a speed of gravitational waves which would depart from 1 at very low frequencies, frequencies comparable to the Hubble parameter today, or wavelength comparable to the observable universe today, and yet be consistent with having a exactly luminal in 1 part to the 15 speed and much larger frequencies comparable to those observed at LIGO. Okay, do you have any questions about this so far? Okay, so let me continue for now. And let me set up the questions. I took quite a while to set up the questions, but once we have them, as always in physics, the hard part is to know what question we like to ask ourselves. And once we get to this point, we actually can make much more progress. So the real question I like to ask myself is the speed of gravity also 1 at low frequency? We know observation tells us it's 1 really, in 1 part to the 50, it's 1 at LIGO frequency. Do we expect, for instance, from symmetry reasons, that it should be 1, exactly 1 at low frequencies as well? Or could it be different? Could it be that there's something happening at lower frequencies, there's some medium or some other effects that come in that doesn't even need to be dark energy per se, anything else that could come in? That means that typically the speed of gravitational waves is not 1. This is the first question, going like this. Oops. And then the second question I like to ask is whether this is even a possibility. Should I allow, so here I put to 1 here, this is the speed as a function of frequency, or energy if you want to. This is not supposed to be 0 and 2. This is maybe 0.9 and 1.1, so it's something like that. I'm not being very too specific. But should we even allow ourselves for this? Does it even make sense to draw a graph where I could have the speed of gravitational waves being superluminal? Maybe we should just discard this from the outset and just focus on something which is physically relevant. Why should I spend my time drawing things which are completely crazy? So the second question I like to ask ourselves is whether we could even think about gravity ever being superluminal. When I say that, I really mean gravitational waves being superluminal, without having some dramatic effects on causality, without having something which is so completely nonsense that I should just discard it from the outset. After all, we know that light travels at the speed of light. It doesn't travel faster than the speed of light. So the same should be true for gravitational waves. Okay, so I'll answer these questions within a framework that we think we understand very well. And so these are the 2 questions I really like to ask myself: whether there's anything to talk about the speed of gravitational waves, or is it 1 always? And if it's not, if it has a chance of not always be 1, am I allowed to even consider superluminalities, or is that just rubbish from the outset, which you think it should be, right? Okay, so I had some motivations on maybe if we observe some departure of the speed of gravitational waves from being exactly luminal, that can tell us something about dark energy, or about the content of the universe, about the dark sector of the universe, or even something quite normal about the universe. So this is what ultimately we would like to achieve. But right now, I just like to have a proof of principle. I'd just like to understand whether within a framework that we know we understand extremely well, there's no what if we add this, what if we add that. It's really something, physics we understand extremely well. What could happen? Because once I establish what happens in something that I understand very well, then I can export that into less known physics, into maybe physics beyond the standard model, or be for the dark sectors of the universe, for instance. What we know we understand very well, or what we think we understand very well, is the standard model of particle physics. So I'm not allowed to write equations. This is not an equation. This is a picture. Okay, this is the standard model of particle physics. If you don't know what that means, don't worry too much. Take it as a cartoon. I don't know exactly. I'm sure you are on a spread level. This is, if you want, this is light. This is the photon living here. These are the fermions. This is the Higgs giving a mass to the fermions, and then this is the Higgs with the potential there, roughly speaking. It's more complicated than that, but roughly speaking, that's the content of the standard model of particle physics that we know. And I'll focus on something even simpler. I'm just going to be mainly focused on the electrons, which are massive. They have a mass here. That's what I like to focus on. So I have massive electrons. Now what I'll do, because I'm interested in gravity, I will add gravity. So we all know there's some issue with quantizing gravity, and maybe you feel very uncomfortable just saying, I take something that I know extremely well, which is the standard model of particle physics, and then I add gravity to it. There's actually no problem doing that whatsoever. There's no problem adding gravity, even quantum mechanically, at low energy. The whole issue with the non-nominalization of gravity, the whole issues with quantum gravity only appear when you're looking at curvature scale, which are close to the Planck scale, or maybe the string scale, maybe a little bit below, but still at very high energy scales. So the Planck scale is 10 to the 18 giga electron volts. Maybe it's a little bit smaller than that, but that's still roughly 15 orders of magnitude beyond processes that happen at the LHC. So beyond processes that we understand extremely well. So all the issues about quantum gravity and our failure understanding precisely how to embed gravity in a fully consistent renormalizable theory, or maybe we do, maybe we don't, I don't know. All of those issues are aspects that we don't need to worry at all about. The aspect about quantum gravity, which will happen close to the Planck scale, 15 orders of magnitude beyond what we're interested in at the moment. If I'm just considering physics related to, for instance, massive electrons. Okay, so there's no issue adding gravity in the game. And so I just expand a little bit my mug. And this is gravity. Again, just take this as a cartoon. This is the content of what we think our universe is made out of. This is the curvature of space-time. This G here represents the metric. This is where gravitational waves are embedded. And then we have the same content I wrote down before, or was written before. There's maybe some axions in here, but don't worry about that. And I'll mainly just be interested in the same massive electrons plus gravity. So coupled to gravity now, that's all, okay? So really nothing dangerous, nothing problematic at all. Okay, so what I'll do is consider electrons coupled to gravity. You can consider photons as well in the game, but I'll do this and I'll try to understand what's going on at different energy scales. So this is my arrow of energy at very high energy. This is where we need to have some completion of quantum gravity. So this is, I'll say it's an unknown high energy completion. Maybe you know what there is here. I'm gonna remain agnostic what's happening at super high energy scales. But then I know that at least at energy scales that we're probing at the LHC, the world or nature is well represented by photons and electrons in the standard model of particle physics, and I can couple them to graviton. There's no problem with that. And then we can also look at what's going on at quite low energy scales. What I mean by quite low energy scales here is, for instance, below the electron mass. And that if I'm working below the electron mass, for instance, I don't need to think of electrons being dynamical. I can just look at the effect on gravity directly. So now I'm going to write some horrendous equations. And again, don't worry too much if you don't understand what they mean, if you've never seen a Lagrangian in your life. It's really just about, sometimes if you think of it as a picture, it's a bit easier to understand what's going on, but I'll show you another way to see it in a second. So this is only for the people that know what it means, and if you don't know, it's okay. So this is my Lagrangian that I mentioned before. So this is the same Lagrangian we had before. So this Lagrangian is what represents the physics we're interested in. It includes gravity, and these are my electrons, for instance. So they have a massive electron. If you're working to very low energy scale, I don't need to think of the electron per se. All I need to do is look at the effect the electron will have on my curvature, and all I have is curvature. So any effect the electron could ever have on my curvature is embedded in curvatures themselves. So this is curvature, and I have higher order curvature, and the scale at which that can happen is related to the scale of this electron, the mass of the electron that comes in. So I have curvature correction that come in when I'm looking at energy scales below the electron mass. This is very symbolic, but don't worry if you don't know anything about those equations. What I'm trying to encapsulate, for if you don't want to look at the equations, is the fact that as you are in a curved space-time and you're looking at the propagation of gravitational waves, if the frequency of those gravitational waves is much smaller than the mass of the electron, then there can be some, there's always, but it's more significant then, there can be some processes where you have some virtual pairs of electrons and positrons going in, and that probes the curvature of your space-time beyond the direct trajectory of the gravitational waves. And so this effect of electrons on the propagation of gravitational waves can mean that it has the curvature of space-time through the electron that exists have an effect on the propagation of gravitational waves. So that happens because you're in a curved space-time, which also have some interactions between gravity and electrons. So gravity and anything else in nature, but I'm taking the electron just as an example. And the effect is carried by the mass of this particle, by the mass of the electron. And so the implications of that, and this is completely standard, this is not my own crazy theory that I just came up with last night and I'm trying to indoctrinate you with. This is completely standard. You can ask any sensible person. It will be the case that the speed of gravitational waves, it is one, but it has curvature corrections to leading order. You'll have some curvature corrections, which if you only account for the effect of the electrons when you are below the electron mass, will be suppressed by the mass of the electron. And this is the Planck scale. So this is relatively small, and this is huge. And then you have all the corrections, higher frequency corrections, so that when you're looking at frequencies which are becoming closer and closer to the electron mass, this goes back to unity. So all of those things resum when you're looking at curvatures and frequencies which are close to this m, so that they all cancel out and you get one exactly. But at frequencies well below the electron mass, you have some corrections to the speed of gravitational waves, which are carried by the curvature itself. And I put a constant here, alpha, because it depends a little bit on the context, and a few things happen. So the actual departure, if you look at the curvature around a black hole, the curvature in the solar system, the curvature due to the expansion of the universe, the curvature of anything you want in the universe, where you can trust GR when you're not inside a black hole, but you remain, for instance, outside a black hole. Anything you want to be considering at all, unless you are during inflation, let's say, in the very early universe, but otherwise anything else at all will give you a very small effect here. So this is not something that's going to be observable directly in the next 1,000 years. This is extremely small. It's extremely small, but it just serves as a proof of principle that there are corrections and there are frequency corrections to the speed of gravitational waves, even in a standard model of gravity. This is standard gravity coupled to standard electrons. There's nothing more standard than that. I'm not being crazy at all. I'm not including anything special. This is just to tell you that in the most naive scenario that you want to imagine, there's no symmetry reason, there's no fundamental reason why the speed of gravitational waves should be identically one to an infinite precision. You do expect tiny, tiny, tiny corrections in the most standard model of gravity, just Einstein's theory of general relativity. Now, if that happens in the most standard theory of general relativity, then you can imagine that as soon as you start adding more elements in the game, these effects can become larger and larger. But that's not where I'm going to, really. Just in the standard case, there will be some small correction. And so in principle, gravitational rainbows do exist. Whether they're observable or not, that's a different question. But in principle, you would expect them to exist. Now, I put an alpha here and I put a curvature square there. Don't be fooled by this curvature square. We're not, the curvature is not a Euclidean quantity. The fact that it's square doesn't mean that it's positive. The curvature can be positive or negative. The curvature square can be positive and negative depending on the space-time. This is all very symbolic. But the typical approach, whether it's to dealing with gravitational waves, whether it's to dealing with light, whether it's to dealing with anything else, is to constrain the type of model that we can allow for ourselves so as to ensure strict subliminality. By strict subliminality, you can ensure it to be zero if you no departure from liminality if you want to, but what I mean by that is absolutely no possibility of going beyond one. So this is where I like to set up a poll and ask you what you think we should do at this stage. It's up to you. You are the generation of the future. You will decide how to analyze our data in the future. Should we put a bound on this parameter, for instance, so as to ensure that the speed of gravitational waves is always subliminal? So I think Chris can set up a poll, is that right? And you can decide whether you think it's, so press yes if you think you should put a bound on alpha to ensure subliminality, and put no otherwise. So can I vote or not? I don't vote, huh?
Yeah, I think we can't vote.
Okay. Okay, very good. So we had 40, 60. I did brainwash you, which is good or bad, I don't know. Okay, 36, 64. I don't know if maybe 2 people haven't voted yet. So exercise your right to vote. Aha, okay. So the last few votes are significant. Okay, there's 1 vote left, but we are getting a fair idea. Okay, good. So we have 67. We have 2/3 of people thinking no, we shouldn't, which is great. I think I set it up so that you would. Probably I wouldn't have asked the question if I didn't want to provoke you a little bit. So I'm very pleased with the result. It is. I mean, should we or should we not? And you would have asked me that question 2 years ago. I would have told you, of course you should. Well, of course you should. No, absolutely, of course you should. And you know, I spent a year redoing some calculations because I was certain I was just messing up things. Because of course, you should end up with everything being consistent, and the speed of gravitational waves should always be subliminal. Until they weren't, and that's what provoked me into trying to understand why they weren't and how that's consistent, or whether I made a mistake. So I think it's good that at this stage, from what you know, there's not a right or wrong answer, and actually probably the right answer is yes, we should most certainly constrain the speed of gravitational waves so that they are not superluminal, so they are luminal or subliminal, because we know, it is well known, that any amount of superluminality is related to a causality. I will review that in a second, but this is typically what we know, what we learn, and what we apply. And we apply that in any type of model that we're considering. And so why not in this case? And this question is relevant because why not in this case, then in all the other cases we've been applying that, were we right or wrong? Is there a reason for that? Okay, so the typical answer is yes, we should put a bound on this parameter. And this is what has been done within our whole community in a lot of the work that we've been doing. So this is what we've done. But there are a few issues when you do that in practice, when you really try to put that, take it at heart and apply such a bound. In practice, there's different issues. The first one is, I just showed you an example where you had massive electrons and you think of the effect on gravitational waves, and it gives you something like that. Here, all I had, this alpha only depended on the field content, it only depended, it's set up. If I only have electrons, this curvature here, I haven't told you exactly, it has different contractions and stuff, but I have no freedom here. There's no alpha there. And so if I want to start having a freedom here, really corresponds to choosing a particular field content. It's telling us that we're not just allowed to have electrons, we're not just allowed to have fermions, we also need to have some bosons at the same mass, and they need to compensate each other in a particular way so that the result, no matter which energy scale you're considering, is always going to give you something which is of a particular sign in here. That requires, this is really expecting that there's a whole structure in the field content in the universe with particular tuning between the various masses of the field content and the spin is in such a way that this can happen. If this were true, then there will be radical in our way of thinking about what nature is made out of, what type of field we can allow for ourselves. This would be really quite different in comparison to what we've done so far. But there's a slightly even more pragmatic issue with that, is that in most of what we've done, the community, they look at a particular case. To be honest, a lot of what's been done so far was looking at what was going on for cosmology and asking that when you're considering the curvature of an expanding or even an accelerating universe, then the speed of gravitational waves be subluminal. But the way the curvature and the curvature square looks like when you're dealing with cosmology and an expanding universe, and the way the curvature looks like near a black hole is extremely different. And sometimes it can be positive or negative here, and sometimes it can be the opposite there. And if you even if you try to make a choice on the field content in such a way that for cosmology, it has the right sign, typically it will have the opposite sign in a black hole context. And so there's no way to win every situation. There's no way to have the speed of gravitational waves always in this context, always being exactly subluminal without having alpha is equal to 0. But alpha is the first order correction in an expansion. So you may set alpha to 0 and that requires some extreme tuning, but then you need the same thing to happen at the next order, etc. So in practice, this is not what's going on. In practice, there will always be a tiny amount of superluminality. And we have to accept that, or what we typically qualify as superluminality, and what we typically use to constrain our type of models when we're doing cosmology. But if we accept that, in principle, we can have a little bit of superluminality, we need to understand why this is consistent with the notion of causality and why we typically like to have subluminality as opposed to subliminality. So yeah, I don't have much more time left. This is going to be quite brief, I think. So just to give you a back of envelope reasoning of what's going on, why we are worried about superluminality in the first place, but why in this particular context it's okay, and understanding why it's okay in this particular context help us understanding how we can apply them in different contexts. So the normal story is, let's imagine, this is very symbolic, let's imagine I'm in flat space-time here, I send in gravitational waves at low frequency, and I send in light, let's say, or gravitational waves at much higher frequency, which travel exactly at the speed of what I qualify the speed of light. So this is the vacuum, they both travel at the same speed. And now I have something going on. I have a blob of matter. This can be a lattice of black holes. It can be whatever puffiness cloud that you have, some type of matter. Really what's important is you have curvature present in here. So you switch on some region in space-time where you have some curvature so as to affect the low energy gravitational waves, the low frequency gravitational waves, in such a way that they travel in a way that you qualify as being superluminal, in the sense that this departure here is positive. So you have this C being larger than 1, and you compare the trajectory to the other modes. It can be the high frequency gravitational waves, or it can be just normal light traveling at a normal speed here. And then you switch off this curvature, you come out of this lattice of black holes, or whatever you've done, and then you see that you have what you call a support outside the light cone. You were able, as compared to where you should have been, you were able to have traveled a larger distance as compared to what you sent in. And it doesn't matter how small, how tiny this violation of luminality you have. As soon as you open the door for this to happen, then in principle, you can imagine a thought experiment, or you can imagine to build up on this tiny amount of superluminality for long enough, in such a way that you always end up with a sufficient large support outside what you would have thought was your light cone. And it's dangerous to have a support outside your light cone. What I mean by a support outside the light cone is that this is a space-time diagram. I have my position here, parameterized by x. I have my time here. I send in a signal. Typically, I can only affect my future light cone, inside my future light cone in here. I cannot affect what's going on in there. So I can't start affecting my past now, and I can't start at the same time as me, I can't start affecting someone located at a different place. But as soon as you can imagine a situation where you can send superluminal gravitational waves in some region of space, you can start having an effect on this point here, which is outside your typical light cone. So far, this doesn't seem completely crazy. So you have superluminalities, and that tells you that the point here, A, can affect the point B. Okay, the issue is now Lorentz invariance is a fundamental symmetry of nature, and we very much like to keep this symmetry of nature. The whole standard model of particle physics is based on this symmetry. It's very well satisfied in everything that we know. By Lorentz invariance, it means that if you have two observers, or you have one at rest and one which travel at a speed compared to the first one, they should be equivalent. And that means that I can boost myself, or I can imagine an observer which is moving with respect to the one on which this diagram was shown, which is moving with respect to the one which sees some position x and time t. That's a boosted observer. And for an observer which is moving with respect to the one I had before, that observer will see a notion of time, which is t prime here, and a notion of space, which is x prime here. So this is something, if you haven't seen special relativity, you will see that soon. This is just a Lorentz transformation. So it's kind of a rotation in a space-time diagram. So if you just had a space, for instance, you would think this is just a rotation. But now it's a rotation in space and time. So that's why it looks like it's tilted. But the notion of light cone here is the same for the Tx diagram as it is for the T prime x prime. But now with respect to this boosted observer, this is her notion of space, this is her notion of time. And so the point B here is actually located in her past. It's located at the position x prime and at the time t prime b, which is smaller than the t prime a. So now, as soon as you believe in Lorentz invariance and that those observers should be equivalent, it tells you that superluminality leads to A affecting B, but A is in the future of B. So for this boosted observer, she's able to affect her past. And this is typically linked to causality. And a priori, it doesn't seem to matter too much what was the amount of superluminality you started with. You can always, as soon as you open the door for that, you can always start having some causality. So how is that possible? in the context of gravitational waves, for instance, in the context of what we call the effective field theory for gravity, to have some sort of what we qualify as superluminality without leading to a causality. And so this is really in the context in which both answers were correct. Whether you answered yes or no, there's something to understand there. I'll be very quick here, and I think I'm really teasing with your patience, so I'll stop very soon. I'm not going to go too much to the details, but if you go through an exact calculation, you will see that no matter what you try to do, no matter how much, if you want to ride on more superluminality, you need to have more curvature, but that kind of takes more space. So no matter what you're trying to do, the amount of support that you can have outside the light cone always ends up being proportional to the whole curvature, and it's suppressed by the mass of the particle you were considering, for instance, the mass of the electron. And you had some effective field theory where these corrections were coming from curvature corrections after having looked at the effect of the electron, and you have higher order corrections. But what I said was this is only true at low frequencies. As you go to higher and higher frequencies, you'll have more and more corrections. It's actually derivative corrections that come in. And as soon as you're looking at derivative corrections, this is really where the frequency comes in. But you made that calculation only assuming that you're working with the leading order terms, not the other high order terms. And so in order to make sure that you can trust your result, you need to make sure that all the other higher terms that come in were under control, so they remain small. If they're not small, then you're not allowed to do something perturbative. You need to resum the whole thing. If you're assuming that they're small, then you need to check that they are small and check the conditions under which all the corrections that you neglected do remain small. And when you do that, you see that this is kind of, this is derivatives, but that corresponds to energy, for instance, energy square, and then curvature has to be smaller than m squared. So it tells you that the curvature times the frequency square over the mass 4 of the electron in here has to be small. Here, the frequency is the inverse of the wavelength. So omega is the frequency, lambda the wavelength, they inverse roughly to each other. I said the speed of light being 1, they're related by the speed of 1 light, and then the 2 pi, I put them under the rug. So that tells you that you can only trust your calculation, and you can trust this trajectory only if you're dealing with a wavelength, a mode that you send with a wavelength which is much larger than the curvature over this mass scale. So that means very small frequencies, very long wavelengths. But when you compare that with the amount of support you can allow for yourself outside your light cone, it tells you that this quantity is actually always smaller than the wavelength of the mode that you send in. But you use a particle approximation to look at this trajectory. You didn't think of something which is delocalized. You really thought of doing a particle approximation, and then you end up with an answer which tells you that, okay, technically, if I trust this, I have an amount of support outside my icon, which is delta L, which is positive, but this amount is smaller than the wavelength of the wave that you were allowed to send in. And so it's not physical. It's not something which is resolvable. It's not something that you're going to be able to detect with a physical experiment at the end of the day here, because it's smaller than even the wave length of the signal you sent in. So in this sense, there's no meaningful propagation outside the light cone, and there's no violation of causality. So as soon as you understand the fact that it's unresolvable, it's not only that you can't conclude anything, then I don't have time to go through it, but then you can go back to your notion of causality and show that it is actually exactly causal through perturbative arguments. So I'm happy to talk more about that later if you want. But yeah, so this is relevant, particularly when you want to do cosmology, understand how to constrain various parameters in the universe. Typically, I'm extrapolating quite a lot here, but just to give you a flavor of where we can go to. This is an example of dark energy with some parameters, C, B, MT, doesn't matter what it is exactly, it just tells you it's a model where you have some dark energy fluid, it interacts with various things, and you can have some various observables. Okay, so these are diagrams with these parameters, and in yellow are observations, are the constraints from observations. Now, if you were to impose the constraints on subluminality, you would conclude that having observations plus prior from subluminality would tell you that you need to be in the yellow region, here. But actually what I'm saying is that what's important is not really subluminality. What's important is causality, and how you impose causality depends. You have to think a little bit about that. It depends a little bit in the gravitational context. And if you try to be a little bit more careful about it, really what you get is the black curves. And combining the notion of causality with observations actually tells you that you should be rather in these black regions. And in some cases, it's quite orthogonal to the notion of subluminality that you had imposed for yourself otherwise. So this is to give you a taste on how relevant this consideration may be when it comes to trying to understanding what's going on in the universe. Okay, so let me just stop here to conclude. Observations at the moment show us no departure from luminality of gravitational waves at all, but it's not to say that this is going to be the case forever. And even in a standard vanilla model of gravity, there's a small technical departure of exact luminality, even though it is tiny. I can show you just as a quick example of what it would mean if you have how you would observe some departure of luminality. I've been talking about gravitational rainbows. What do I mean by gravitational rainbows? I'm not going to see a gravitational rainbow in the sky. What do I mean when I talk about gravitational rainbow? So this is very much accentuated, but imagine you look at the signal from a black hole merger or a neutron star merger, but at much lower frequencies than the one that have been observed by LIGO. So let's imagine you do that from LISA, but still you'd expect a signal of this form. So this is the signal that has been emitted. But if you have a gravitational rainbow, let's say, the lower frequencies, if you think of the lower frequencies traveling slower than the higher frequencies, so the lower frequencies are being sent first, the higher frequencies are being sent later. If the lower frequency travel faster than the higher frequency, for instance, then you would see the signal as being compressed. So this is how you would observe a gravitational rainbow if the lower frequency travel slower. And then vice versa, if you had some level of what you would otherwise qualify as superluminality, then it would be stretched. And if you were to emphasize that very much, then this signal could even flip, right? You could have the high frequency mode traveling so much faster than the lower one, then this could arrive before that. I mean, this isn't going to happen. It's just to be extravagant, to give you some taste of what it is you're looking for when you talk about that. Okay, and then just to conclude, you can in principle have some very small notion of what you would otherwise qualify as superluminality, and in some cases you shouldn't constrain your models so as to prevent those superluminalities. Really, you should go and tackle the very notion of causality, and then sometimes the notion of causality allow for yourself some level of superluminality. If you want to be a little bit more technical, you can see more how much an amount of superluminality you can allow for yourself and be consistent with causality. This is roughly the formula, but this is more if you're interested in it. Okay, I'll stop here. Thank you for your time.
Awesome. Yeah, thank you so much for this wonderful and raising some really big questions to think about. And it's been just a great talk. I guess now we'll turn to audience questions, if anyone has any. Andre, you want to go ahead?
Yeah, thank you for the talk, first of all. That was great. I was thinking that parameter alpha, which is like the source of all the evil and like superluminality and stuff, is it not derivable from first principles of like that Lagrangian that you had? Can you not write it from like physical constants and stuff?
Yeah, so sometimes you can, and sometimes it's a bit more complicated. But indeed, it would. I can't go back. Yeah, you're absolutely right that in principle, if you just had, forget for a second the issues with quantum gravity at very high energy, but you just thought you had, let me go here. let's imagine you just had that. This is your theory of everything. This can never be your theory of everything because you have quantum gravity at very high energy. So it always has to be suppressed by, you have corrections that will come in relevant here. But let's ignore that for a second. Let's imagine this is all you had. Then these are determined. They're exactly determined. And so in the context of, for instance, if you just had an electron, you know exactly what those corrections would be, and you have no freedom to play with. You can't decide whether or not you want it to be 0 or positive or negative. They are what they are. Now, what I was trying to say is that maybe you can fudge what you end up with by saying, well, there may be other sectors, there may be other fields which we don't know, there may be some dark sectors, and not even talking about dark energy or dark matter. Everything couples to gravity. There may be other things I don't know that come in with exactly the same mass as the electron, and that affects those terms there. I can't deny that, and priori that could happen, and maybe asking for those terms not to be exactly what I had from the electron, for instance, may tell you that you need to have something else there. And if this is the logic, and I think that's a very beautiful logic that one can follow, and it would be powerful because it would tell you that it's a way, it's kind of a particle accelerator in its own right. It's a way to decipher the field content that connects with gravity at any energy scale. But from what we know from the standard model, it would just be fixed, and so you don't have so much freedom to a first instance. Now you also know that there is some unknown physics in here, and that cascades down to, it's possible you may say, well, actually, I already had some curvature corrections here that I simply hadn't probed. And so when you look at what's going on at very low energy, is the contribution of the curvature corrections I already had there, plus those of generated by the electron. And all I know is the sum of them. All I can probe is the sum of them, but the electron just contribute to part of it, and I don't have the whole instance of it. But yes, typically for those type of corrections, you imagine they are dominated by the lightest massive field that you're looking at the contribution from. And so if you have very high, very, very massive field beyond the standard model, their contributions to the next order leading terms here would be irrelevant.
So if you don't do any fudging, is that alpha positive? So that's the problem with like superluminality.
It's so the thing is, this alpha here, yes, if you don't do any fudging, you can always end up with situation where it can be positive, and some other situation where, sorry, I should say, that whole thing here will you can always end up in a situation where you have superluminalities if you don't do any fudging. That's right.
Okay, Andrew.
Hi, thanks for the talk. I had a question regarding your plot, kind of showing how the distribution of potential speeds widens up at lower frequencies. To my knowledge, the pulsar timing arrays generally are looking for a stochastic gravitational wave background, like nanograv. So what would evidence of a non-luminal speed of gravitational waves look like for an experiment like that, if it were to be detected?
Yes, so very good. I put it here like the pulsar timing array. It's more to show you the frequency of what you could have. These are the frequency of the modes you could look like. Now you like to understand how much of a handle on the speed you would be able to get from a pulsar timing array. From pulsar timing array, I mean, you don't account for the distance between the signal and the propagation to you. It's more about the size the array, of the pulsar array, which would be important. So I don't know how much of a handle on the speed they could have, but in principle, this is a type of things you can imagine, indeed, that at LIGO frequency, you could have a signal which is very close to luminal, but open up the possibility to having a small departure from luminalities in different for different instruments, for different observations. So what people may consider is, for instance, at LISA, you can imagine even a same event happening and then being captured quite early on in the merger at LISA frequencies. And then later on, it could even be a year later, as the system has reached much higher frequencies, seeing it through the eyes of LIGO. And so that could give you a handle on what, for the same signal, you would get in terms of the speed at LIGO frequency to the speed of LISA. Now, if you really start having multiple data points in this graph, it's going to very quickly, and I suspect it's going to be very close to 1 at the end of the day. I'm not telling you what the error bars here are. I mean, maybe it's 10 to the minus 15 still, or something like that. But it's just to tell you that at the moment we have 1 data point on this graph, and in principle you would expect things to depend on the frequency.
Thank you.
I have one question that's perhaps a very naive question. But why would we expect the speed of gravity to match the speed of light in the first place? Is there a good intuition for this?
Yeah, so it's I guess, let me see. So when I say that, it's really at high frequency, and I guess part of the rest of the talk is to say, well, you shouldn't maybe at lower frequency. But so first of all, at high frequency, when you go to sufficiently high frequency, no matter what the curvature of your spacetime is, if you zoom to short enough distances, and so to frequency which are large enough, it should look like flat spacetime. Are you happy with that first idea? Yeah, so if you're happy with that, then that means that at sufficiently high frequencies, everything looks like flat space-time, and also whatever medium or matter or whatever there was in your space-time, it will look like the distance between the atoms and the interaction scale with the electrons or whatever is going to be too weak to have any effect. And so you really just in flat space-time, and you have a massless particle in flat space-time, being the graviton, being the photon, and all they can do is travel along the light cone. It's just related to the notion that they don't have the notion of proper time, or I don't know how you learned it in special relativity, but massless particle just travel along the null geodesics, if it were. That's just related to the notion of time invariant as soon as you have Lorentz invariance. Yeah, so as soon as you have flat space-time. But it's really because they are massless. If they were massive, then of course you open up a whole new discussion. But still, the effect of the mass only comes in at frequencies related to the mass. And so that's quite small frequencies still. And it always, the mass is a dragger, right? It is always slowing you down as opposed to spinning you up as well. So when you have a mass, you're going to end up being inside your light cone as opposed to on the light cone, but you don't expect to suddenly start going outside the light cone unless it's a tachyonic mass, and that's just an instability. But of course, we don't want that for light or for gravitational waves.
Cool. I think we have one more raised hand. We probably should make this our final question. We're running a little bit past time.
Yeah, so just a quick name question. So when you said that delta L is proportional to root of curvature by m square, shouldn't it also be proportional to the distance, and increasing the distance we can possibly get it to be greater than lambda, because lambda does not depend on distance?
Yes, so that's what we would think, right? It's a little bit more subtle than that. So if you want to go through the details, it's an excellent question. So I've gone very quickly through that. And the answer is no. At the end, I mean, this is symbolic. It's really symbolic. So there's a notion of distance that comes in. So you're talking about that right here. Why you think this is the ratio, or this is related to the angle, and then I multiply that by the length. This is already a length. This is not an angle. This is already a length. So the thing is, you're trying to compensate increasing the amount of superluminality with increasing the distance. But if you want to increase the amount of superluminality, you need to increase the curvature. But in increasing the curvature, you can stack, if you want. The easiest way to think of them, for instance, is to stack black holes next to each other, so as to do that for a longer period. But for you to be able to trust that, you need to spread also the black holes far enough, and so you're reducing, you're actually reducing the effect. So at the end of the day, even in the best case scenario, it does work out, and trying to increase your level of superluminality will reduce the overall distance. You can trust that for. Or if you want to increase the amount of distance or the amount of time, you can trust yourself into this region. It comes at the price of reducing the curvature, and therefore reducing the amount of superluminality, and therefore reducing the amount of support outside the light cone. But I can point, so if you go on the archive, and you'll be able to see our papers on that, and we have 2 papers with Tolly. You can look at this paper there. Have a look at this paper on the archive, and then we go through that in the context of cosmology and in the context of black holes. And it's not going to be, the answer is not that. It's not as simple as this. You probably won't recognize that. But if you go through the argumentation, you'll see how whatever situation you're looking at, actually you can't win into having something which always ends up being proportional to the distance. It's not quite as simple as that. Yeah, so have a look at the details here.
Awesome. Thank you so much for joining us today for this wonderful talk, for staying after and fielding all these questions.
Thank you all for your interest.
Absolutely. And thanks to everyone else for attending. And we'll see everyone next week.
Have a nice week. Thank you, everyone.